Alrighty everyone, Monday, and today we are starting quantum mechanics in earnest, which is going to take us throughout pretty much the rest of the semester. Now we're going to start out kind of slowly. In fact, I'm even going to spend about 10 minutes going over some observations that were made back in the I forgot, 1920s or something, that got people to start thinking about quantum mechanics, which means to think about matter as waves. It's also part of your general education. Some class business first. Don't forget that your exam, is now really quite close. Next week, I think. So that means that we won't have an extra hour. Instead, we're going to have 2 lectures, and the Wednesday before the exam, we'll have a review. And the review, of course, I will focus heavily on what's on the exam because I wrote the exam fresh, which is why those of you who are looking at last year's exam are going to fail. You're going to be answering the wrong question, so that's not going to work too well. Let's see, I also got a note from the university. Let's see, something from a lawyer. Cease and desist was something about not talking about the animals in the lecture centers. Is it still there? All right, moving on. Matter as waves. Okay, how does that work? Back in the day before dinosaurs were confined to zoos, or giraffes for that matter, people started studying heat capacities. Almost lost my ability to spell there. Okay. People started studying heat capacities because heat capacity measurements are pretty easy to make. And people were starting to figure out thermodynamics. And this is around 1900 or so. People started to figure out what internal energy was. A few years ago, they just figured out what entropy is, right? So all this stuff is coming together. And I hope you remember this one. You did just have this class. The change in internal energy with respect to, I better double check, temperature at constant volume is of course the heat capacity at constant volume. All right, now you know from the equal partition theorem that I brought up a couple of times that the internal energy is 1/2, let's use RT, instead of K, normally I like KBT, but let's use RT. Times degree of freedom, and I'm going to use shorthand, DOF, degree of freedom. So, therefore, look how easy it is. It's right, 1/2 RT degrees of freedom. Now, that's why argon, my favorite thing, argon, right? It has 3 translations. It can't rotate or vibrate. So, did I put a T? Oh my God. Anyway, oh my God, it sounded like a value. Okay, so that is why argon has a heat capacity of it's like 12 point something joules per k mole, and because and that would be 3/2 R. 3/2 R. That's the heat capacity. Something like N2 or O2 would have 3 translations plus 2 rotations, right? So that would be 5/2 R heat capacity. And then something like methane, which has 3 rotations, no vibrations, 3 rotations and 3 translations, has 3 R heat capacity. Okay, so anyway, just a trip down memory lane. Now let's think about this object. Let me draw it, digital. And what you see, of course, is a brick. I'll write that, a brick. So what I'm really trying to be funny is it's a solid. Let's do the heat capacity of a solid. Now, you may be thinking whatever, but here's my point. Degrees of freedom for, again, let's go back to argon. That was pretty easy. 3 translations. Think about the atoms moving around. That's not hard. But bricks are made of atoms, so let me draw an atom in the brick. And you know that it's basically connected by springs. It's connected by springs to the other atoms. And I'll represent that like that, because there's more than one other atom. Okay, so the atoms are connected by bonds, which are little springs, to all the other atoms. So, okay, I guess it could vibrate. Yeah, that sounds good. Translation is vibration. What about rotate? Well, again, I'm sure I'm doing some animation, right? I could pick up the brick and toss it. Is that a rotation? Kind of, yeah. Here's my point. This is actually really freaking hard, right? I mean, it should be easy, but it's not. I'm not sure what a degree of freedom is for a solid, because we're always thinking about the atoms, and I don't know if this thing can really rotate, right? So this was kind of confusing, and the people who figured this out are Dulong and Petit. So this is Dulong and Petit's law. These guys are French, which I know is disappointing, but so I'm probably mispronouncing it. That's my point. Oh God, this is like, geez, this is like early 1800s, by the way. So what they figured out was that the degrees of freedom are, let's see, they are kinetic energy and potential. Okay, so the way that works is the atoms are on little springs, right? Now they're vibrating, and they can vibrate in 3 dimensions, right? Obviously, up, down, left, right, and then of course, in and out of the board. So there's 3 dimensions to vibrate. But why doesn't it just shoot out, right? Well, it's because it's on a little spring, and if the spring gets pulled hard enough, then the atom will stop moving and it gets snapped back. Well, what's the difference between motion? It becomes difficult to distinguish between kinetic energy and potential energy because they keep transferring amongst each other. So they decided that potential energy was also a degree of freedom. The ability to move and the ability to stretch and compress the spring, which are the bonds. So they said the degrees of freedom of solids is 6, and therefore the heat capacity at constant volume is actually 3R. Okay, that's great. So here's what happens. Okay, what we're going to do is now way back when, people are building the first refrigerators, and people are able to, this guy named Joke, he built refrigerators that got down to like the 1 or 2 Kelvin area, right, near absolute zero. Won a Nobel Prize for it. In fact, I got my PhD working in Joke Hall. Anyway, so I met him. No, just kidding. He died before my grandfather was born. Anyway, so here is. Let me put 3R on this graph, and here's temperature, and here's 0. What you find is that for a solid, is that, the heat capacity is around 3R until you get close to absolute 0. So the graph is at 0, 0. Until you get close to lower temperatures. When you get close to 1 or 2 Kelvin, all of a sudden the heat capacity just basically disappears. So the question that people had was, well, I get the 3R deal at higher temperature. Why? Basically, are like the degrees of freedom. Where are they going? Because 1/2 R isn't changing. That's for certain. So the degrees of freedom are changing if you get cold, and the heat capacity goes down as a result. Now, hopefully you're thinking like, well, if the atom's frozen, it can't move anymore. Good, right? And that's a good way to think about it. But here's the deal. They want to have we want to derive things that are like perfect, that describe this exactly. Einstein was the first person to do so. Not the first person, but he got close. First person to get close. I'm just hoping to spell it right. And his idea was that the heat capacity is a function of temperature, is 3r in a rather complex function. I'm not going to write it down, doesn't matter. He was thinking of these atoms vibrating, and they vibrate with h frequency. And of course, that's going to be, as usual, if you're going to divide out by kBt. So Einstein has this idea that the heat capacity of a solid is 3r times some function of frequency, which is the frequency that the atom vibrates in its cage, and is like, you're hopefully sick to death of seeing, of course, that's also divided by kT. H nu, H frequency is energy, so of course we divide by kBt. It's kind of a complicated function. I don't want to write it down. It doesn't matter. How did it work? Well, look at that. Look at that. See how close that is? See how close that is? That's great, isn't it? Isn't that great? Isn't that great? It's not great. It's not perfect. But there needs to be, oh, maybe I'm doing some digital right now. I'm doing some digital. Now I have to do the digital. Anyway, it's not 100% right. And they felt back in the day that it had to be 100% right. Okay, now, what's the real answer? Debye, this guy Debye, he saw it. And so this is like a big deal because this is how solids work, right? Also remember, like, the way to get things to superconduct, of course, you know, wires are solids, and you often have to freeze them, right? So this is kind of part of that. Anyway, so Debye solves the problem, and he gets it exactly right. So I won't draw a graph on top of another graph, but he gets it exactly right. Here was the solution. All right, now you take what Einstein does. Einstein has the vibrational frequency of the solid. That is what Debye realized was a mistake. There's more than one frequency. And here's how this works. And the point is that, in terms of our relation to quantum mechanics, is that Debye is thinking of atoms as waves. And having this in people's minds allowed them to eventually figure out quantum mechanics, which was only a few years away. So how does that work? So these are the atoms in a solid, right? It's crude, but anyway. What he realized is that you could have very low frequency type motion, right? So what I've done is, it's a wave, right? It's like a wave in a stadium, and the atoms are like people in the stadium, and everyone's taking their turn standing up. So it's like this, right? And all the atoms are contributing. Now that's a rather long wavelength wave, right? This is as long as the material. That would be the longest wavelength you could have. Kind of like how the longest wave that fits in a light bulb is the size of the light bulb. So we see that behavior here. Now where Debye really gets it right, really got it right, I have to wipe all this out, I have to redraw it, is that he realized that there's an upper wavelength. We see what the lower wavelength is, but there's an upper one too. He realized that you really can't do better than this in terms of frequency, right? Okay, so now I'm drawing that wave. And you see how the atoms, they're all moving out of phase, every one next to each other. And you can see that the wavelength is basically the distance between two atoms. And that's the shortest wavelength you can have. Now, when Debye plugs that information, that there's long wavelength and that there's a short wavelength and there's limits, then he was able to calculate the heat capacity of solid perfectly. It's absolutely perfect. Now, here's the thing. The reason that there's a cutoff, I just want to show you this. So I'm going to focus in on this guy again. Here, so let me draw this wave again. So just follow along with me, Harry. So let me draw the wave first, and you'll see why in a minute. Okay, I'm going to draw the wave first, and I'm going to make the atoms conform to that. Up, down, up, down. Okay, again, that's the shortest wavelength. As opposed to a wavelength that's not allowed, oh God, trust me, this is kind of hard to get. Okay, what's going on there? There you go. Okay, my question to you is, this is a shorter wavelength, obviously. It's obviously wavier. But does it exist? The answer is no, because this wave describes this motion, but this wave, it also describes the motion, but how can you tell? How could you tell? This frequency is twice as much as this one, but this one describes the motion perfectly. Now so does this wave, but how could you tell the difference between these two? The answer is you can't. And so, for lack of a better description, this one wins. This is artificial. It's artificial to say that you could have, the reason is ultimately is because the wavelength is now shorter than the distance between bonds. How could you do that? It just inherently doesn't make sense. So this shows you why this is the cutoff. That's the upper frequency. All right. Anyway, now the point of all this is, for one, to be blunt, your general education. This is the Dulong-Petit law. I'm sure that's French anyway. It tells you about how heat capacity of solids work. That's important for superconductivity because superconductivity requires cooling things. So anyway, the Debye model of solids is very important. It describes heat capacity correctly. But like I say, it gets people back in the 1920s to start thinking about matter in waves together, which was brand new. It's just rattling around in people's heads, and that's a very good thing. You solve most of your problems subconsciously. That's why when you're at the exam and you have a problem with the question, leave it alone. Come back to it, because your head back here is solving it, but you need to give it time. And that's what was going on in the 1920s with this guy, Louis de Broglie. So now quantum mechanics, and quantum mechanics starts really with Einstein, and I'm going to write that. I'm going to explain that in a second. But what happens is this guy Louis de Broglie, and I know it's spelled de Broglie. It's pronounced de Broglie. Don't look like an idiot. Okay, it's de Broglie. De Broglie takes some of Einstein's lessons and he converts them into what became quantum mechanics. So that's why I'm writing his name down first. And I'm going to write down what Einstein came up with, which de Broglie changed in a minute. Okay, de Broglie, he lived to 100 years old back in the day, so you know he had no teeth. I just want you to know that. He had his first PhD in history, and the second PhD, because why not, was in quantum theory. He got his PhD at 32. His thesis could not be understood by the people evaluating his thesis at his university, so they had to send it to Einstein to be evaluated. He didn't believe it, but he gave him a pass anyway. And that's at 32 years old, and at 37, he got a Nobel Prize. All right, so how did he do it? What did he do? He takes something from Einstein. What did Einstein come up with? Einstein came up with E equals mc squared. Actually, he didn't. I believe this is on your homework. That is a simplification of the actual equation. Did you know that that is not the real equation? This is the real equation. And I believe that's on your homework. That's the actual equation that Einstein derived for the theory of relativity. Now you can see why people had a bit of a time with this. It's not simple, but notice that for an object not moving, if P is momentum, if an object's not moving, then I have E squared m squared c to the fourth, which simplifies to mc squared. So E equals mc squared is the theory of relativity for an object at rest, but nothing is ever at rest, so that's not the right equation. Anyway, Einstein spits this out, de Broglie takes it. One of the cool things about this deal is for a photon, remember we just talked quite a bit about photons. Photons have no mass, so let's get rid of that guy. And what you find is that E squared, which is, I know it's redundant, for a photon is h squared c squared over lambda squared is equal to c squared p squared. C's cancel, and therefore, this is a bit of a feat, isn't it? Momentum is h over lambda. Okay. So one of the amazing things about Einstein's equation is that, again, we dropped this because photons don't have mass, yada, yada, yada. Photons have momentum. Photons have momentum, which is Planck's constant over their wavelength. Remember when we talked about the photoelectric effect? That photons are like marbles hitting electrons, which are like other marbles. So they can knock them out of that silicon. Remember that? Oh, okay, I guess I'm doing the effects. Light knocks those electrons out. It conserves energy, but it conserves momentum too. Everything has to conserve energy and momentum, just like that last extra hour I talked about. So light has to have momentum, and there it is. That's why the photoelectric effect works. That's why Einstein got a Nobel Prize. Okay, here's what de Broglie does with this. I'm kind of not working this correctly. Einstein says the momentum of light is this. De Broglie says the wavelength of matter is this. So if light can have momentum, then matter can have a wavelength. Light has momentum, and momentum is something we think about as mass times velocity. That's a thing for things that have mass. So de Broglie says, well, if things that have mass have momentum, therefore they would also have a wavelength. Now, I'm sure the derivation was a little bit more complicated than what I just saw. I don't think you would have been able to fill the thesis. But de Broglie's idea is that matter has an associated wavelength depending on how fast it's going. And in fact, people have measured this. In fact, this was a big science article in 1999 at MIT. They got buckyballs, right, C60, and they shot these buckyballs through a diffraction grating. I actually met the guys that did it. Diffraction grating made of silicon. So that was actually the brilliance was they had to make a diffraction grating out of a piece of silicon, so they had to etch little slits through it. And you know what? It diffracted. So what they saw was they had some kind of detector for mass, and they could see that they had a kind of a typical light, like a diffraction pattern which you would think you would get for light, but it was for mass. Okay, so de Broglie is correct. Matter does have a wavelength, and it is measurable. Now here's the thing, though. The reason that you generally don't notice this, and this is part of your homework, is that the de Broglie wavelength, if you think of heavy objects as having a lot of momentum compared to a light object, the de Broglie wavelength of me is really small. Like really, really, really small. Smaller than an atom. If a wavelength of a thing, like this thing, or that thing, is smaller than an atom, how would you ever know it? How could you measure it? How could you measure something smaller than an atom when everything you have to measure are made out of atoms, right? You can't. You don't know that it's there. Okay, but when things get lighter and the momentum becomes smaller, the wavelengths get larger, and then you can measure them, right? Once things become the size of the tools that we can measure things with, then you can measure them, right? It's really that simple. So that's why things like electrons, those are very easy to measure the diffraction pattern from. Okay, so here's the deal. De Broglie comes up with this. Matter has a wave. Now this is rolling around Schrodinger's head, Erwin Schrodinger. Also a guy named Heisenberg. Heisenberg actually came up with quantum mechanics before Schrodinger, and he wrote a paper before Schrodinger, but he wrote the mathematics in a more complicated way. It's kind of funny. Schrodinger did not discover quantum mechanics, Heisenberg did. Well, they really did it at the same time, but people understood Schrodinger's equation quite a bit better. What is the Schrodinger equation, which you know is going to be the subject of the next 2 months of your life? The damnedest thing is, I just taught a class on graduate quantum mechanics, and I was going to derive it, and it turns out that Schrodinger died before he told anyone how he did it. So people are having to guess at how Schrodinger derived the Schrodinger equation. They think they know how he did it, but the damnedest thing was, when the guy published the Schrodinger equation, everyone started applying it, and they never thought to ask him how he did it, and then he died. He also had 2 wives. Anyway, I'm not kidding. He actually had a lot of problems because he had 2 wives, and a lot of people weren't okay with that back in the day. I'll tell you more gossip about the rich and famous and dead some other time. But here's how the Schrodinger equation works. Let me write that down. When I'm not trashing his character, the way that the Schrodinger equation works, this isn't the real derivation, but it gets the point across, is you can think of this as kinetic plus potential, this is going to blow your mind, equals total energy. Right, mind-blowing, right? Well, the actual derivation is a bit more complicated. But this is a good, this will work. All right, kinetic energy. Now this guy was actually more of a physicist. And I know in chemistry we like to say kinetic energy is 1/2 mv squared. I like that. But they like to put things as momentum squared over 2m. And I think on your homework you were going to verify that p squared over 2m, remember p is momentum, mv. M squared v squared over 2m is 1/2 mv squared, right? So the units work out. That's joules. And again, you're going to do that on the homework. Plus v is equal to E. So there we go. All right, now I can go ahead and tell you that for the next 2 weeks, we're going to work with particles, no more argon, like just an electron, and there won't be any potential energy. So, fine. So we're going to have p squared over 2m is equal to the energy. Okay, whatever. Next step. We know from de Broglie that p squared better be h squared over lambda squared. Okay, fine. This thing has got to work with that. And I know that's like, well, how in God's name are we going to do that? All right, hold on. The next thing we have to work with is the wave nature of light. So I better have a wave equation. All right, so my model for it, again, I'm just going to go ahead and tell you now, to make this introduction to quantum as easy as possible, we're going to talk about an electron. It's by itself, so there's no potential energy. It's just a single particle. There's nothing else in the universe. The universe is empty. And it's one-dimensional too, right? It's just all in the x direction. So a single particle by itself in the x direction. That's our universe, and we're going to solve quantum mechanics for that. Because if we can't do that, we can't do anything. Okay, now that thing, I need a model for it. And it better be a wave model, because this is what we're talking about, waves. I got to have this lambda in there. Okay, so my model, I'm gonna make it a wave. I'm gonna make it a cosine. And as usual, we know that when x goes from 0 to the wavelength, cosine better go from 0 to 2 pi. So I've just written down this wave description of this electron off the top of my head. I didn't derive it, but it has to be correct. When a particle goes from 0 to its wavelength, the cosine goes from 0 to 2 pi. So I know that this is right. Now, let me simplify this. Let me call this just, because why not? Let me call that kx, where k is, of course, 2 pi over lambda. And it's called a wave vector. This is way more important than it just appeared right now. Let me say that again. K, 2 pi over lambda, is a wave vector. It is something you are going to see every class period for the next 2 months. This is the most important thing that I've told you as of right now. So it's not hard to remember, okay? Technically, let me give it a little bit of a face. Technically, it points in the direction that the wave is going. So think about I think it was on those diagrams. Remember when I was talking about left and right circularly polarized light? The axis that it's traveling is the k vector. Anyway, so this thing has a lot of meaning. And you're going to see that, trust me. All right. Well, here, let me go ahead and do something with it. Okay, so p squared over 2m. Let's see, what do we do with this? All right, so I know that, okay, let me take out the 2m, And p squared is h squared over lambda squared. Okay, now what I'm going to do is I am going to, okay, the 2m doesn't do anything. What I'm going to do is I'm going to take h squared and I'm going to divide by 2 pi squared. Then I'm going to multiply by 2 pi squared. And then I've got lambda squared. Now look at that. K is 2 pi over lambda, so k squared is 2 pi squared over lambda squared. Now another thing to note is that, as I think a lot of you have probably seen before, this thing called h bar is h over 2 pi. We do this little symbology because if we didn't, let me preview again, h is in all of our equations, and so it's 2 pi. H and 2 pi, they're always together. So, to avoid the unbelievably annoying fact of having to write down h over 2 pi over and over and over and over again, somebody said, let's just call that h bar and forget about it. Right. Okay, so now what do we got? Now I've got h bar squared, no, we're not that, k squared over 2m. Equal, remember, we're not doing any potential energy, is equal to E. Okay, so this relationship is cool with the de Broglie relation, with de Broglie's equation, right? All right, now here's the deal. What we've got to do is get this thing to spill this information. That is what Schrodinger has to figure out how to do. How do you make this give you that? Now there's a second little deal here, and this is kind of cool. This gives me goosebumps. I'm going to write down the Schrodinger equation now in the actual form. It turns out Schrodinger knew a little bit more. They think, again, they don't really know what he knew or what he didn't know. But it turns out that, of course, the mathematics of music, say that again in case the sound got messed up. The mathematics of music was very well known. And guess what? It uses differential equations. The mathematics of strings, of vibrating strings, was very well known. People were able to mathematically describe violins and pianos and the frequencies that a string would make. Right? Standing waves. I think you have some idea what that is. All right? So, Schrodinger knows about the mathematics, the differential equations that describe how strings vibrate. We have the de Broglie relation, we have this cosine kx, and we know what the energy should be. So all he has to do is get all this stuff in his head and write something that makes it all work together. Now, you may be thinking like, well, how could I ever do that? I don't know. If you could, maybe you're going to get a Nobel Prize like him. But if you can't do it, we're not all going to win Nobel Prizes. Not even me. Anyway, so let's see. What did he come up with? All right, here's the idea. You want to operate. You want to do something to cosine kx to give you, let's say, we want it to spell out k squared. Okay. This is what you want to do. You want to get the thing to spill its guts. Now notice that I wrote cosine on the left and right. That is characteristic of a differential equation. Differential equations are the equations used to describe musical instruments. So you see how we're killing a lot of birds with just one stone here. We're getting k squared out, and we set up a differential equation looking thing, which should be right to describe strings. All we have to do is figure out what this operation thing is. Well, I mean, I think it's kind of bloody obvious, right? Let's do a double derivative. Double derivative. Okay. Double derivative of cosine is indeed my k squared, gave it away. K squared cosine kx, actually it's minus. It's minus, right? Double derivative of cosine. Derivative of cosine is minus sine. Derivative of sine is cosine. Okay, well we don't want that minus there, so let's put the minus up there. All right, we're almost there. Okay, now we want this thing, it's spit out k squared, but what I really want is energy, right? And actually, all I need are a bunch of constants. So if I put just minus h bar squared over 2m, then I get h bar squared over 2m. And look at that. If I cancel out the cosines, what I've got is energy. There you go. So Schrodinger's equation, this is Schrodinger's equation, we figured it out. Minus h bar squared over 2m, double derivative of some kind of mathematical model for our thing is equal to the energy times that same function. That was the idea. Okay, now you notice I gave a little space. That's in case there is a potential, then you would do the same thing. Okay, now again, for the most part, there won't be anything there. Potential energy. Let's not worry about this. It won't be there for all the examples we're going to spend a lot of time on. So anyway, I don't want you to freak out about that. It's actually very easy. We're going to start easy. Minus h bar squared over 2m double derivative is equal to e times the same function. That function we're going to call a wave function. It has a couple of different names, unfortunately. It's also called an eigenfunction. It's called an eigenvector. It has a couple of names. I won't worry. I'll try not to say that too much, but it's called a wave function. And here you go. This is Schrodinger's equation, and unfortunately it's a Diffie-Q, right? It's technically, because that's a double derivative, it's technically a second order differential equation, and that is painful for all the reasons that you're going to spend 2 months covering. This guy is called the kinetic energy operator. So get used to that word, operator. Operators are going to be things that alter wave functions. To alter a wave function, we're always going to see one of two things. Either we're going to take a derivative of the wave function, and a double derivative is just a derivative twice. Or we'll take the wave function and multiply it by like x. So we can multiply by x, which changes a function to a new function, or we can take the derivative of the function, which changes it to a new function, right? Now, in the wave equation, notice that, okay, let me go ahead and just get rid of that, because we're not going to worry about this for quite some time. Now, the way that the Schrodinger equation works, it's also a bit painful, is that when you do this kinetic energy operator on the wave function, it still has to come back, right? So you can see why solving this can be a bit of a pain. The double derivative of what is equal to a constant times itself? What kind of function does that? Cosine does, right? So it's not impossible, obviously. Cosine does, sine does. E to the x does. Looks like I got a bunch of these. And guess what? You can multiply them and add them together. Cosine plus sine is a valid wave function. Anyway, we got a bunch of these to work with. Last bit. There's one more thing that we can get out of this, which is, let's see here. If I have, we can figure out what k is. I can put a little bit more of a picture of what k is using this information. Right now I have the Schrodinger equation, and I have a wave equation of cosine kx. Just like that Planck problem, remember how I wrote down the differential equation for the Planck distribution, right, the Maxwell equation deal. And then I told you what the electric field equation was. And then I put that back into the Diffie-Q, and I got more answers out of it. This is how this works. I've got the Schrodinger equation, I've got a wave function. Now what I do is I put the wave function back in the Schrodinger equation, and I can learn more stuff. And that is how this class goes for the next 2 months. A wave equation, usually it's Diffie-Q, so I'll give you the solution, we plug it back in, and we learn new things, useful things. Just like how a light bulb, how the energy is just how hot it gets. That's useful, right? right? And so that's how all of this works. All right, so what am I going to do here? What I'm going to do is change this around pretty easily by moving the constants over to one side. Okay, so what am I going to do? I'm going to take the double derivative of the wave function. And that is going to be energy, but I got to take care of the constants. So I've just brought them over to the right side. And minus times the wave function. Oh, that E looks terrible. I better fix that there. That's a nice looking E. Okay. All right, so what? Well, let's work on cosine. So double derivative. And what I'm doing, by the way, is I'm going to figure out what K is. Oh, that looks awful. Sorry, my handwriting is kind of bad. Okay, what is this? All right, well, we know that this is minus K squared cos Kx is equal to minus 2me over h bar squared cos Kx. Okay, the cosines cancel out, the minuses cancel out, and what you find is that cosine is now square root of 2me over h bar squared. Now I know what K is. Now remember that K is also equal to 2 pi, is equal to, sorry, messed up. K, no, I didn't. What's wrong with me? It's just late. 2 pi over lambda. Right, so now I even have a really nice way to figure out what the de Broglie wavelength is of a particle depending on its mass and how much energy it has. So, I'm getting all kinds of stuff. Okay, last bit, because I want to end a little bit early, just a minute or two early. Let me show you one last neat thing, and that just ties it all together. I want to make sure that the de Broglie relationship hasn't gotten messed up. So remember, all this started with the de Broglie relationship. Just think of matter as waves. Einstein amalgamates all this stuff, and from all this stuff, we're here. Well, we better make sure that we didn't lose anything along the way. So here's what I'm going to do. Okay, so if this is K, sorry, I painted myself into a corner, haven't I? Okay, h bar squared, K squared over 2m is the energy, and energy is still momentum squared over 2m. Okay, now what I want to do with this is I want to make sure that I can still find the de Broglie relationship between momentum and wavelength. This better still work, right? This is the end of that derivation I just did, and this was more at the beginning. So I want to make sure that all this still works, all right? So what I do is, okay, so I have h bar squared, which is h over 2 pi squared. K squared is 2 pi squared over lambda squared. The 2m's cancel, is equal to p squared. So h squared over lambda squared is p squared, which means that, of course, p is h over lambda, which is the de Broglie relationship. Okay, so it all works out. So again, from the Schrodinger equation, here, assuming that the wave function is of the form cosine kx, which you can't get more simple, I'm able to figure out what k is. We also know that that better be 2 pi over lambda, or the wave isn't being a wave. And sure enough, if I assume all that, I find that the de Broglie relationship is satisfied. So I know that's kind of a lot to put in your head. Don't worry about it. I'm not going to have you derive all this on an exam. This took me, 20 minutes? So it's not on an exam. I just want you to take home Schrodinger equation, wave equation, Diffie-Q, that's the main thing. And what we're going to do from here on out are describe models, particles in a box. Remember that from the last, the extra hour? Bonds, vibrations, hydrogen atoms. We're going to have models that are going to go in the Schrodinger equation. We're going to get wave functions. Often I'll have to give them to you because, again, the math is kind of hideous. So I'll just say, by the way, here's the wave function. We plug the wave function back into the Schrodinger equation, and then we learn incredibly microscopic details of atoms and bonds and whatnot that you could never have figured out any other way. But once you know this stuff, you can test it and find that it's all true. So that's the big picture of this class. Okay, so I know that this has been quite a bit, and I'm over time. So next time on Wednesday, we're going to start talking more about wave functions. And as I said several times, we're going to spend about 2 weeks just talking about cosine kx. Next class, I'm going to tell you what does it mean for matter to have a wave function. What does the wave function mean? So that will be the next class. All right, so I've hit my time limit, so that is that for today, and I will see you all on Wednesday.